In this demonstration, we'll show how electromagnetic induction works. We have today a coil of wire. You can see that coil of wire right here. It has electrical connections on the top and the bottom. This is a long coil of wire. There's an opening down the middle so we can stick things inside it and see what happens. The wires, in turn, are connected to a galvanometer. This is a very sensitive ammeter. It will measure current, positive or negative 500 microamps. So if there's some phenomenon that will cause this current to flow, we'll see that here. The way we get electromagnetic induction is to have a magnet moving through this coil of wire. What you need for electromagnetic induction is a magnetic field, a length of wire, and a velocity, one of them moving relative to the other. So let's get a magnet. Here I have a magnet. I've got North Pole in red, South Pole in blue. I'm going to plunge the magnet into the coil of wire. As I do that, observe the galvanometer deflecting. As I push it down in, you'll see it moves to the right. I pull it back out, it'll come to the left. If I move it very slowly, there's just a small amount of current. If I pull it out slowly, it'd be a little bit of negative current. Fast move down, you get bigger jump. Fast move up, you get a big jump. Now I can take this magnet, flip it around, have the South Pole down instead of the North Pole. Now if I come down into it, you'll see a negative pulse. Coming back out will be positive. Negative in, positive out. Again, flip it around, North Pole in, positive pulse, negative. The greater the speed, the greater the current. There's one other thing that we could change. Instead of using this little nickel magnet, I can take a neodymium magnet, much greater magnetic field, much stronger magnet. If I push that in here, look what happens to the galvanometer. Bonk, bonk, wonk, wonk. Big change. Bigger magnetic field, huge change. I can move this guy very slowly now. It's a big magnet, so I move it slowly. You're still going to see a lot of current. If I change direction, bring it out, I'm going to see positive current. So I have the South Pole down on this one, obviously. And that is electromagnetic induction from a magnet moving through a coil of wire. Instead of having a magnet move through a wire, I could have a wire move through a magnet. You see we have this large magnet here with our north and south poles. I'm going to take the length of this wire, move it through the magnetic field. As I do, observe the galvanometer deflect very slightly. It's a small effect because I only have one loop of wire here. If I flip the loop around, I'll get it going the opposite direction. And I can move it quickly to get a bigger deflection. It goes very slowly, you'll see almost nothing. With a single loop of wire, it's going to be a very, very small effect. To get a larger current, what I can do is instead of having a single wire going through it, I can take this coil that has 200 turns of wire. So we've increased the length by 200 times, we're going to see a lot more current. I'm going to move this very slowly through the magnetic field. You see the galvanometer is really responding strong. I could kill this thing if I hit it too hard, so I'm going to very gently go back and forth through it. So there's a huge effect pushing this 200 turns of wire through the magnetic field. This is such a large effect, I could actually light a light bulb by moving this coil back and forth through the magnetic field. Observe. We can observe the same thing with an LED, the light-emitting diode. The thing with an LED, the current will only flow one direction. So in this case, if I take the coil and move it downward through the magnet, it lights up. If I come back up, there's no light. Down, lights, up, no light. If I flip the coil around, I'll reverse the direction of the current flow. Now we'll see no light when I come down. Bring up, lights up. And there you have it. That's electromagnetic induction.